Okay, so the chapter number 8, as I just give you introduction. So starting with the sine wave, hope you have idea about the sinusoidal waveform. So this sine wave is basically is all the full form is a sinusoidal wave. In short, we call it sine wave. Is a basically fundamental alternating current. In short, we call it AC, and alternating voltage waveform. So if you just look here, the shape of sinusoidal wave, this is the shape. So here on x-axis we are having time, on y-axis we can have voltage or we can have current. Okay, similarly we have negative y-axis here, negative values of the voltage and current. So it is same for the voltage, it is same for the current, any waveform shape. So here we have a positive maxima, we have a negative maxima. So the values are same, but for one is positive, another one is negative. Okay, so that's why the alternating current. So these maxima and minima, it's continue and it is alternating, positive, negative, and so on. So electrical sine waves are named from the mathematical function with the same shape, basically. Okay, so the shape is sine, so electrical sine wave are named the same as the name, same shape name like sinusoidal wave. Like the wave, maybe you have observed, if you throw a stone into the water, you can see there are waveform generated, wavelets generated at that time. So you can see the waveforms which is basically creating in the water when you throw a stone over there. But in electrical, electrical waves, you cannot say check see that one with your naked eyes. So we need to have some devices where we can see these electrical signals, otherwise we cannot see that one. So what is just mentioned here? So sine wave is wave is a disturbance. What in general, unlike water waves, electrical waves cannot be seen directly, but they have similar characteristics. Like all periodic waves can be constructed from the sine wave. So there are different kind of periodic waveforms, like it is like a square wave or a rectangular wave. They can be generated by using sine waves. So at the end of the chapter, I'll show you by using sine wave, how can we construct other type of wave like square wave or rectangular wave. So which is why the sine wave is called fundamental. That this is the reason, that's why we call the sine wave as a fundamental wave. So look here, sine waves, more detailed characteristic. Sine wave are characterized by the amplitude and the period. So there are two things. One is amplitude, another thing is the period. So the amplitude is the maximum value of the voltage or current. It is a maximum value of the voltage and current. Okay, so if I just ask you guys, where is the maximum value? So yes, you can check it. The maximum value is at the peak of this, either positive or negative. Okay, so if you just look to the center of this point, and if we just measure this one, so we will find that this is the maximum value, which is 20 volts. Okay, so this is something. So amplitude is basically denoted by a letter called A, letter A of this sine wave, 20 volts. Okay, we can see here it is basically the amplitude. Another thing is the period. Okay, and what is the period? Period is the time interval for one complete cycle. Now you can say, what is a complete cycle? Whom you will call it is a complete cycle. Complete cycle is basically constructing of one positive maxima, one negative maxima. So this is called a complete cycle. Yani we are starting from this point and ending at the same point. So this is called a complete cycle. So what is a period? Period is basically time required to complete a cycle. It's called the time period. Okay, so this is about the amplitude and the period. So now if we just ask, okay, what is the period here? So we can see that the time is given already here, and we can see that starting with the 0 microsecond, the unit is also mentioned, and it is completing this complete cycle in 50 microsecond. So that period is 50 microsecond. Okay, So amplitude is basically measured at the center here. We can see, and period is measured along the x-axis, time required to complete a cycle. So the period is basically, it is not necessary that we will always measure the period like this one. We just start this show to you. So we are starting from this point and ending with this point. So it doesn't mean we will always measure. Okay, there are alternative ways also to measure the period. Like if you look here, the period of a sine wave can be measured between any two corresponding points on the waveforms. Like I can measure that period from peak to peak, any positive peak to positive another peak. So the time required to reach this one is also a period. It's same value. Similarly, I can start with the negative cycling start here, this point, and corresponding point is this one. So we can also measure time period 0 to 0. Okay, so peak to peak, 0 to 0, it's possible. Now negative peak to negative peak. So peak to peak measurement is also possible. So these are the different points, two corresponding points where we can measure the time period. Okay, regardless of the amplitude will always be measured from the center of the peak, basically. So by contrast, the amplitude of the sine wave is only measured from the center of the maximum point. Now the next thing comes here, the frequency. Okay, frequency is denoted by the lowercase letter f, and frequency is the number of cycles that a sine wave completes in 1 second. Frequency is the number of cycles that a sine wave completes in 1 cycle. So in 1 second. So in 1 second, how many cycles are completing? That is called the frequency. And the unit of the frequency is the hertz. So for example, if I just give an example here for this question, if 3 cycles of a wave occur in 1 second, the frequency is. So you can see here, see, so we are starting from here and 1 cycle complete. Second cycle complete. Third cycle complete. So 3 cycles completed. And how much time is required? 1 second. So it's clear that the frequency is 3 hertz, because in 1 second, 3 cycles are completing. So answer is 3 hertz. So period and frequency relation now. So the period of a frequency are reciprocal of each other. Means if you know the time period, you know the time required to complete 1 cycle, and frequency. So they are inversely proportional to each other. If you know one, you can use the another one. Thus, if you know one, you can easily find the another one. So if the period is 50 microsecond, the frequency is, so we know that the period is given. So if period is given, so period is basically 50 microsecond. Here is a point, yani the unit conversion, which you need to take care. You know already about the unit conversion. So they are asking here the frequency. So we know that f is equal to 1 over t. So the t is given to you here. 50 microsecond. All right, so we can just put it 50, and micro means 10's power minus 6. So 10's power minus 6 will go up, and this is 50, and 10's power 6 yani 6 zeros. It's like that over 50. This 1 0 will cancel this 1 0, and by using this 5, this 10 will go 2 times. Remaining zeros 1 2 3 4. So either you can say 20 kilo hertz, or we can also say 0.02 megahertz. Okay, so this is the way. This way you can calculate the frequency for the given time period. Sine wave voltage and current values. So there are several ways to specify the voltage of a sinusoidal waveform. The amplitude of a sine wave is also called the peak value. What is that? The amplitude. So amplitude of a sine wave is also called a peak value. Yani amplitude, we discuss about the amplitude. It is denoted by the A. It is also called as the peak value, because what is the peak value? The maximum value, and it is abbreviated by the VP. Okay, so for the waveform. So like again, we are having a question the peak voltage of this waveform is, okay, so peak voltage yani the voltage which is measured from the center. So we know this center of a peak, this is that one, and we can see it is corresponding to 20 volts. So either we can say voltage amplitude, or we can say peak value. They both are same thing. So peak value is denoted by the VP. So you can see this one, it is 20 volts basically. Okay. Next thing comes, guys, here is you need to focus more, it is important point. It is RMS value. RMS yani stand for root mean square. What is RMS stand for? Root mean square value. So the RMS value of a sinusoidal voltage is equal to a DC voltage. What's that? The RMS value of a sinusoidal wave voltage is equal to the DC voltage. Guys, the earlier the formulas which we discussed, power formula and others, power and all, so they are basically for the DC. But here we are discussing the alternating current, voltage or current. So we can have equivalent DC voltage or equivalent DC current for the given AC values. So how can we convert the AC into equivalent DC? So this is RMS here. RMS will help you to convert AC into DC voltage. This is something, okay? So now how can we convert it? For example, if you know the peak value of the AC, okay, and you multiply with the 0.707, you will be getting VRMS, which is basically the DC equivalent of the given AC. Now, maybe if you just look at VRMS is equal to 0.707 VP, okay, same way as I said, so voltage and current formulas are same. What is the change? Bus I will change. So IRMS here will be IP, yani peak value of the current. Here you have VRMS, any peak value of the voltage. So this is the formula. So here, guys, this value, which is 0.707, is coming basically. Yes.
Can you repeat what you said RMS stands for?
Root mean square.
Root mean?
Root mean square.
Okay. Thank you.
Root mean square. Okay. So here is a thing like a VRMS. So this maybe this value is difficult for you to memorize. I will give you another way to memorize it. You can remember like VRMS is equal to 1 over root 2 or VP over root 2. Can you check this one by using your calculator? Are you getting the same? 1 over root 2 means 0.707. Similarly, you can write it IRMS, root mean square. So this is IP over root 2. Check it, this one. With the calculator, 1 over under root 2. Are you getting 0.707? Yes. Okay. So this is the thing, yani. Okay. This is root 2, ROOT. Root. So root mean square is basically this way. So this is easier compared to that one to memorize. So you can memorize this way. So guys, the thing is, if one thing is given, we can find another thing. It's just, vice versa. For example, if you want to calculate VP, so VP, you can cross multiply. So you can say, guys, VP is equal to under root 2 VRMS. Similarly, for the current, you can say IP is equal to under root 2 IRMS, like that. Okay. So these are the formulas which is important. You can note it down. Other way, this will come like that. So I think better, this is easier in terms of under root 2 to memorize compared to the 1414, but it is the same thing. It's up to you what you like it. Accordingly you can proceed. There are some YouTube links for via RMS values understanding. You can just check that. So another term here comes, guys, which is called peak to peak. Okay, so the voltage of a sine wave can also be specified as either peak to peak or RMS values. The peak to peak is the twice of the peak value. We discussed already what is the peak value. Yani from here to here, it is called VP. But what is VPP? VPP stand for twice of VPP. VP basically, it's a double of it because it is peak to peak. So here, if I ask you guys, okay, what is the peak to peak voltage? So you will measure it from one peak to another peak, which you will be getting 40 volts. So this is also one term which is called peak to peak. Now, so RMS voltage they are asking. All right, if they are asking our RMS voltage, so I can simply say VRMS is equal to VP over under root 2. VP over under root 2. Or guys, we know that from here, if you want to write this one, so we can also say VP is equal to VPP over 2. So if I put this value in this equation, so I can also write this one VPP over 2 root 2. Okay, so the thing is, if you know one thing, you can just interchange these things. Okay. Okay, we were discussing about the root mean square value also. So here is the any point. If you calculate the this RMS value of this one, so you can see this what we are getting basically. So peak to peak is basically this measurement, but when you get it RMS, so I told you RMS is basically tells you the DC equivalent value. So DC yani direct current. So direct current waveforms, guys, is a constant. There is no alternation. Its value is always fixed. For example, if we have voltage here, we have time here, we are saying 5 volts, yani its value is constant, always 5 volt. But in AC, it's keep on changing. You can look here, right? So after getting RMS, as I told you, the RMS value is gives you the DC equivalent of the given AC. So this is a constant value. This is like that. So it is 14.1. Yani DC equivalent of this given AC voltage. One more term come here after the RMS or VPP, which is called the average value. Now you look here, average value. So guys, if in general, if I ask you guys, what will be the average value of this waveform, yani starting from here and up to here? What is the average value? Average, and you know that addition and divide by the 2. So when you get the average value, will you be getting a 0 or not? Because you have one positive, one negative. So they will cancel each other. So the average value for the whole cycle yani up to here, it will always be 0. We know that point. Okay. So this is about the average value for the complete cycle. But now guys, that's why the average value of the sine wave when taken over a complete cycle is always 0. So we measure the average value for the half cycle. Okay, half cycle, yani up to here, for example, from here to here. In order to measure the average value, how we will be calculating this one? We will be calculating by this formula. The average is equal to 0.637 VP. Now again point comes 0.637. How would you remember it? Okay, so I will give you again a best way to memorize this one. So as I said, VP is measured from the center. Okay guys, and you also know that this is complete revolution will take 360 degrees. How much? It is called 360 degree. You have idea about it. Or we can show this one in radians. Do you remember that? We can also say this is called 2 pi. It will take 2 pi to complete a cycle. If you can measure, show this one. 2 pi radians. Okay, so if it is a complete cycle 2 pi, so how much will be the half? Will it be pi or not? 180 degree or pi? Yeah, 1 pi. And what will be the at the center? It will be pi by 2. Okay, so you have idea about it. So as I said, the average value is given taken for the just only one half, not the complete cycle. Just we got it for the half waveform. So we are taking from the center. So V average AVG formula is like that. VP, and where you are measuring? You are measuring from the center of the peak. Any it is pi by 2. Pi by 2. Okay, and you know that 2 is a denominator. When it is flipped, you what will you be getting? You will be getting 2 VP over pi. Guys, can you check it? 2 over pi, 2 over pi. Is it coming 0.637? If coming, so I think it is easier to you to memorize like that. Check this one. 2 over pi. Same value are coming. Okay. So it's easier, right? And also 2 over pi. And you know that what is 2 VP? Do you have? Remember that we just discussed twice of the peak value. What is that? Can we say it is VPP? Okay, so VAVG average, this is the formula. Either we can express in peak to peak, or we can say twice VP over pi. So this is called the average. Now this is for the voltage. Similarly, this is for the current. Voltage will replace by the current. So this is the average. So what we learn, we discuss here VRMS, IRMS, VP, VPP, V average, and like that up to here. Now, so for some purpose, the average value, actually the half wave average, see they are mentioning here, half wave average is used to specify the voltage or current. By definition, the average value is 0.6 time of this peak value. Now guys, I can ask you, the average value of the sinusoidal voltage is, so average, no problem, you know the formula. The peak value is 20 divided by pi by 2, you will be getting the answer. Okay, 12.7 volts. This is the what we call V average. Both are different, you know that, VRMS and V average. Next thing comes angular measurement of a sine wave. So angular measurements can be made in degrees, or it is measured in radians, guys. Okay, so the radian, yani we show in short we write RAD, radian is an angle that is formed when the arc is equal to the radius. What is the arc? This is called the arc. Okay, when this arc is equal to the radius, it is called 1 radian. Understand? So there are 360 degrees or 2 pi radians in one complete revolution. Okay, so 1 radian is equal to 57.3 degrees. Now the thing comes, this is the waveform as I mentioned to you. In radians, it is basically shown as here in radians. It is 2 pi to complete half cycle, yani pi, then middle of it 2 pi, pi by 2, and again pi by 4, it is equivalent to 45 degree. Now again, there is a reference YouTube video, you can check it there. So there are 2 pi radians in one complete revolution and 360 degrees in one revolution. To find the number of radians given the number of degrees, for example, we can give you degree now and we can ask you guys how much radians are there. So there is a need to convert degrees and to radians. So we can do it easily by knowing this just relation. And what is the relation? Radians will be equal to 2 pi over 360 degrees. Okay, so just put here degrees, which is given to you, and then it will be 2 pi over 360 and radians, and then you can get it like that. Or you can simplify this one because this is a 2. So if you just divide this 360, you will be getting 180. So the formula comes how much? Pi over 180 multiplied by the degrees which is given to you, and you can get it. This one. So this is the formula. Radians equal to pi over 180 degrees. Also, guys, vice versa possible. Yani we can ask you how much is the degrees for the given radians. All right, no problem. So you can say 180 over pi multiplied by radians. So vice versa is also possible. This is like that. Degree is equal to 180 over pi and radian. So question may come like that. How many radians are in 45 degrees? Okay, simple. Just put in the formula. Pi over 180 multiplied by degrees. So this type of questions are possible based on the formula. So questions are straightforward in this chapter. You should know the formulas. How many degrees are in 1.2 radians? Again, it's simple. You can just put the formula 180 over pi and just put there how many radians. You will be getting the answer like 69 degrees. Okay, so they are simple, but you need to memorize here formulas. Next thing comes, guys, which is sine wave equation. So earlier, examples we have seen that we can find the value of a sine wave. For example, when the angle is 2 pi, so we can say, okay, the value is 0. We can easily identify when the angle is pi, we can say it's 0. We can easily identify when it is at that center, any pi by 2. How much is the value? You can say the voltage is equal to A. But what if, guys, we wanna check the voltage or current at any instant, yani here, any place for the any given angle. So for that we have an equation. This equation is called instantaneous voltage uh, equation. So here small letter V stand for instantaneous value, Vp is stand for the peak value, and sine theta. So theta is angle in radian or it is in degrees, like that. So by just putting the angle and putting the value of the peak, we can easily find what is the instantaneous value of that voltage or current. Similarly, we can also write for the current. So current will be I is equal to Ip sine theta. So current equation like that. So for example, if the theta is like that, so when you put that angle, you will be getting, okay, this is the value. Like that we can measure. So if the peak voltage is 25 volts, the instantaneous voltage at 50 degrees. Okay, so we will put in this equation and we can find how much is the instantaneous voltage. So you just put Vp is equal to 25 and theta is equal to 50, and then you will be getting this 19.2 volts, like that. Because you know that the maximum value is 25. Definitely it will be less than or equal to of this value, instantaneous voltage. So 19.2 we are getting.
Doctor,
Yes.
how did we get the degrees?
Which degrees?
50 degrees for the sine.
So it is given. It is given in the question.
Okay.
It is given. It is a question now for you. If the peak voltage is 25, it is given. And when the voltage at 50 degrees,
Okay.
it is a question. Nah? So you put these value
I
here.
thought that was the answer. My bad.
Okay, no problem. So it's simple. You can easily get it. All right. Now you look here. So a plot of the given previous slide, a peak value is basically 25. We know that what we discussed, we are discussing now again. The instantaneous voltage at 50 degree is 19.2 volts as previously calculated. So here is 0 degree here and 50 will be falling somewhere here, and we just measure that value and how much this is coming instantaneous value and how much it is coming 19.2 volts. So this is something. So this way we can show the vector here. So this vector is basically showing the degrees. So starting with the 0 degree, then 90 degree, then 180 degree, and then here 270 degrees, like that. So how this vector is rotating? Look, so as you are moving further, so this vector is moving, rotating anti-clockwise. When you reach to the center, you can see the center value is this one, and this is basically 90 degree. So this vector will reach here at this point, and it will be identifying this way. So here we are showing this yani instantaneous value with the vector, and this angle is basically the theta. Okay, look now. So the thing is, the vector is now pointing to the 0 degree. Yani this is yellow. You can just look here, point, which is showing that degree is 0. So the vector position will be like that. When you move the degree to the 45, the angle, this vector will rotate like that. When you reach to the 90 degree, so vector will be straight like that position. Okay, the angle is forming this time. How much is the angle? 90, because here is the 90, you can see. Now 135, 180, then like that, 270. So we can show this one with the help of phasor diagram. Okay, what it called phasor. So the sine wave can be expressed as the projection of a vector rotating as a constant rate. The rotating vector is called a phasor. What it called? A phasor. So rotating vector is called a phasor. Phasor are useful for showing the phase relationship in AC circuits. Now guys, here is a point I need your attention. So here we have different waveforms, and we want to see how are they related. Other waveforms are related. So we have two waveforms, waveform A and waveform B. Here we try to know what is the relations of these waveforms. So if you look, the waveform A is starting from the origin, okay, but B is starting from the this point. So how we can relate them? So here we can say, guys, and we know that as we are moving on this way, this is the time axis, and time is increasing. So if we look here closely, which waveform is starting earlier, A or B? Which waveform is starting earlier? So if you look, you will find that A is starting earlier, okay? Then B is starting after 90 degrees. So what is the relation? How can we say? So we can say that A leads B. A is leading because it's starting early. So A is leads B by how much? 90. Because this difference is a 90-degree difference. So we can say A leads B by 90. Similarly, guys, we can also say that B lags A by 90. Because this is here, B lags A by 90. Are you getting this point, guys? Either we can say A is leading by 90, or we can say B is lagging or lags A by 90. Look this relation now here. So if you look here closely, who is starting earlier? So A is starting here, but B is starting before that point also. So this time, who is leading? Who is leading? Who started earlier? A or B? A or B? If you look, this is starting before the A. Okay. So what we will say? B leads A. How much? 90, because degree is given. Also, we can say A lags B by 90. A lags B by 90. So this way, by knowing the phase angles, we can identify, we can relate the given waveforms. This is the way. So here we discuss about the phase concept, phase shifting concept. So what is this phase shift? So phase is a sine wave of a sine wave is an angular measurement that specifies the position of a sine wave relative to a reference. Position of a sine wave relative to a reference, to show that a sine wave is shifted to the left or right to that reference. Okay, so we use phase shift, whether it is shifted to the left or right to the reference. A term is added to the equation previously given. So we know already instantaneous equation, it was Vp sine theta. So now we are adding one more component there, which is called the phase shift. So it will tell you whether this equation is in phase with the reference. If it is in phase, phi will be 0. Is it out of phase? Yani it is left side or right side. So this phi will tell. So this is the phase shift. Let's take an example to understand. Yani how can we find the value of phi? Look here. So the blue one is our reference waveform. Reference waveform. You can see this reference waveform is starting from the origin, this point, and red one is our example, our waveform here, which we are try to find what is the phase difference. So in this example, guys, you can see that the example of the wave that lacks the reference. So we will try to find here reference. Okay. So look now here. So we can identify, we can write the equation for it, and it is basically V is equal to, what is the peak? You can see the peak is 40, and we can write sine, and what is the angle? Theta. What about the phase? Phase, because it's starting from the 0 point, it is given by that. So this is our reference equation. Reference equation, right? Now we want to write this, the equation for this, the given waveform. So here we can see that instantaneous value will be 30. 30 is this one. This is a peak value, and then sine. And now we need to find the phi. Here is a phi, because here in this case phi is 0 because it's starting from this point. But this one is now phi value. So how will you know that what is the value of phi? Phi value is this point, is starting point, and its origin where it is crossing this one. And this difference is basically how much? 45 degrees. Now, you know that whether it is leading or lagging, you can see that reference is starting at this angle, but another waveform is starting late. Yani, we can say that the waveform is lag the reference by 45 degree. So lag, it shows with the negative sign. So we will be writing theta, 30 volts, 30 sine theta minus 45. Okay. So this is about the phase, lead and lag. So this example is for the lag. Now you look here, notice here the point that the lagging sine wave is below the axis at 0. You can see that if any waveform is lagging, you will find that it will touch, okay, the negative axis. So you can quickly identify, okay, this is the lag waveform, which is lags with the reference. And the equation has a negative phase shift. Equation has a negative phase shift. Now let's have an example of the leading waveform. Okay, see the leading waveform. So the red one now is starting earlier than the reference. Reference is starting with the origin. We know that, but it is advanced here. So the equation will be 30 sine theta plus 45. So here the term comes plus because of its leads. So here we will say that this red waveform is leads the reference by 45. Okay, what is the point here to be noted? First point, we notice that the lead sine wave is above the axis. So you will see that it will be crossing this positive axis, positive y-axis. So it is one of the, or you can say, point to identify that whether the waveform is leading or lagging. So this way we can say it's lead. Another thing, the equations has a positive phase shift. So you will also find that the equation is having positive phase shift. Now guys, here is the examples for you. So hope it is concepts is clear. Now I am asking you write the waveforms for the uh, given picture. If we write the equation for the given waveforms, how many waveforms are given to you in this example?
3.
3. Okay, so we need their equations now. We need their equation. So what is the equation for A? What is equation for B? What is equation for C? Do you remember the form? VP sine theta plus minus 5.
10 sine 90 maybe for
10 sine
90
by 90.
because it's on its peak.
What about the
Uh,
peak? It's not about the peak.
the angle is under its peak, right?
10 sine theta. And you know, here it is plus minus 5. This is the equation. But if you look here, it is starting from the origin. So what is the value of phi? Phi is 0. So you will write simply 10 sine theta because phi value is 0. So it is not required. This is the equation, 10 sine theta. Similarly, for the B, if you check the B, this is 20 and somewhere here is minus 10, for example. Okay, now you check for the B. What is the equation for the B? So B is basically peak value is 8 sine theta. Now you check for the B. B is lag or leads with the reference. Your reference is the one which is, starting from the 0 axis. Yani A is your reference. So you check for the B. B leads or lag the reference, yani starting earlier or later, or you know that it is crossing the positive or the negative axis. So what is the example now? B is leading or lagging the reference. Is this leading or lagging? It means you people are not listening. All right. So here leading, I already told you that if it is starting earlier than the reference, it means it leads. Also, I already told you if it is crossing the positive axis, it is leads. So here we will be having positive, and how much it is leading, you need to check this angle from the 0 reference because up to here is 20 given. So the half is will be 10. So it will be sine theta 10. This is the equation for the B. Similarly, equation for the C. If you look C is starting late now. It means, so this is called leads, and another one is lags. Why lags? Because it is starting late here. And it is also crossing the negative axis. I already give you the property. So here the answer is 5. Sorry, this is about the C. So C is 8. This should be 5 for the B. So sine, this is the B. So theta minus 45. This is the lag waveform. So these are the A, B, C waveforms and their equations and their phase relations. So this is the reference which is in phase. B is leads. That's why the sign is here. How much leads? 10. And this is lags. How much lag? 45. So this way you can identify the waveform equations. Okay, guys, clear up to here? So this is here basically power in resistive AC circuits. Before that, we have calculated the power in DC circuits, but here we are going to discuss about how can we calculate the power in a resistive AC circuits. So guys, as I told you, you remember, hope, all the formulas which we discussed for the power for DC circuits. There are three formulas. It was P is equal to V into I, P is equal to I into I square into R, and P is equal to V square over R. These are the formulas. But these formulas are for the DC circuits, right? DC circuits. Now, how can we apply these formula for the AC circuits? So these all formulas are applicable for the AC circuit, but provided your voltage and currents must be calculated in RMS values. You know that how can we get the RMS, VRMS? So if you know the peak value, then you can just simply calculate it RMS by root 2. Similarly, you can calculate IRMS, which is equal to IP over root 2. So you will be given peak values. You can calculate the IRMS values. Then you can apply the same formulas, but you should have in RMS. So P is equal to VRMS into IRMS, VRMS square over R, okay, or IRMS square into R. Formulas are same. You don't need to memorize anything, but what you need to know, you should use the RMS values. And I told you that getting the RMS values means you are getting DC equivalent values for the given AC. Then you can apply these things. Okay, this is the point here. So as I told you that RMS values are basically equivalent for the AC. For example, guys, if we have an DC, this is the DC symbol, you know that, and we are having 120 volt DC. Okay, look here, this is the AC symbol, AC source, AC voltage source. So here, if you are having a signal with the peak value of 120, 170 peak, okay, and if you try to get its RMS value, you will see that this is equivalent to this DC actually, and this signal will produce the same power to this bulb, which is this DC source is producing or giving. So 170 VP, when you get its RMS value, you are getting 120 VRMS, which is equivalent to this one. So same, yani either you use 120 DC source to energize this bulb, or you use 170 peak AC signal voltage to energize this. They will produce the same power. Okay, this is just for your information. So assume a sine wave with a peak value of 40 volts is applied to a 100 volt resistive load. What is the power dissipated? So you have given peak value. So first, your aim is to get VRMS, which is VP over root 2. VP is given 40 divided by root 2. Then R is already given. So you can calculate P is equal to VRMS square over R. And then you can calculate it. Okay, look here now. So you get first, you need to get it first RMS. After getting this one, then 28.3. Yes, Ali, correct. And then you can calculate the power. So power is 8 watt basically. Okay. Similarly, guys, one more concepts come in this continuation of AC and DC. Actually, you know, this AC and DC, both type of signals, you know, usually present in any circuit. So when it is a situation when we have AC and DC both present in any circuit, so what will happen? The frequently DC and AC voltages are together in a waveform. If both are together in a waveform, they can be added algebraically. They can be added algebraically to produce a composite waveform of an AC voltage riding on a DC voltage. Riding on a DC voltage. Yani, for example, we have a circuit, there is only AC, there is no DC. So you will be having a waveform like that, where it is swinging. If you look, this is 0. So this voltage or current is swinging around the 0 axis when there is only AC, no DC. And what about the DC waveform? A DC, you know that if this is 0 axis, this is voltage, and we are showing some DC voltage. So this will be something somewhere here. Okay, but when this one and this one both present in any circuit, so what will happen? The AC signal will ride on the DC. It will not be riding on this 0 no more. It will be riding on the DC. So what will be having? You will be having something like that. So this AC, this is AC, right? And this is DC. So now AC is riding over the DC. It's not, swinging around the 0 axis. It is now shifted to the DC level. So this is your DC voltage. And then how can you find this maximum value? So maximum will be calculated by the formula VDC plus VP. Similarly, you can calculate the minimum value of composite waveform, which will be VDC, yani this one, minus VP. So this is the situation, guys, when VDC is greater than the peak value. So all the composite waveform here is shifted above the 0 axis, above this 0 axis. But what if DC is less than VP? If this is less than VP, so you will be getting something like that. So maximum point will be VDC plus VP. Minimum will be VDC minus VP, because VDC is lower than VP. So this time you will be getting this negative value. That's why the signal is some portion of this negative peak is below the 0. Okay, this is like that. So this is the composite waveforms, this one and this one, two situation. First situation, when the VDC is greater than VP, so complete waveform is above the 0 axis. Another case, when VDC is less than VP, so some portion is of this peak is under this 0. And this depend upon what value you are getting as a minimum. So VDC minus VP. This is basically superimposed DC and AC voltages. Now, consider it with an example. Read the question. So determine the maximum and the minimum value voltage across the resistor in each circuit of the figure and show the resulting waveform. So if you look this figure, you will find that there are two sources. First is AC. This is the symbol of AC source. Another one is DC. And now they are asking you to calculate how much is the minimum and how much is the maximum voltage across the resistor. Okay, it's simple. So you know VP is 10, VDC is 12. So you can calculate the maximum value, Vmax, because it's a series circuit. So complete voltage will be across the resistor, because only one resistor here we have. So VDC plus VP, you are getting positive 22 volts. You can get it minimum value, VDC minus VP, and you will be getting, and you can see here, what is that? DC is greater than VP. That's why both values are positive. So if we draw this the waveform, composite waveform, resulting waveform, it will be like that. So this is the 0 axis, minimum value is 2, maximum value is 22, and this is the DC voltage, which is given to you already. How much? 12, this one. So this is the composite waveform. Okay, so this example is clear to all of you. Okay, so this type of questions may come. We can ask you to draw the waveform or find this one. So you know these things, how to do it. Okay, guys, so this topic is about non-sinusoidal waveforms. So before that, we have discussed the sine waves, its property, and all these things. This is basically non-sinusoidals, yani the waveforms which are not sine, they are different shapes. So pulse waveforms comes in this category. Basically, a pulse can be described as a very rapid transition leading edge, we call leading edge, from one voltage or a current baseline to the another level. Then after the interval of time, a very rapid transition trailing edge back to the original base value. So these transitions is in levels are called the steps. Okay, what is pulse waveform? Just come to that one point. I will explain here to you. So look, this is called the pulse waveform. And what we have in the pulse waveform, we have a leading edge. What we have, a leading edge. This edge is called the leading edge. You can see the name, or we also called rising edge, because the value of this pulse is increasing from here to increasing up. That's why leading. When it has some constant value, now it is decreasing. So what we call falling edge, or we call trailing edge. Okay. Now this is called the amplitude. The height of the pulse is called the amplitude, and this is called the baseline, yani from which voltage it is starting. This is called positive going pulse. Another example of the negative going pulse, because it has some base value, it is going negatively, reducing here. So if we show just arrow, it is then going to negative value, and then it contains value, then it's going up. So it is increasing now. So this is its falling edge, this is its rising edge, amplitude, and all this. So this is called ideal pulses. Now, why we are saying ideal pulses? We are saying ideal pulses. Reason is that, guys, you look here at the same time. At the same time here, we are saying that this is basically, now it has some value. For example, if I say the base is 0 volts. So, guys, from this 0, it is reaching to, for example, if it is 1 volts. See, it is suddenly changing here, this value. But practically, it is not possible. Yani changing a value from 0 to 1. Voltage should raise, with taking some time, but should not be quick or transition. So this is just ideal case is possible, but in reality, it should take some time. Yani it should rise like this, or then constant value. Then after changing from 1 to 0, it should again take some value, yani some time. This is like that. So this is showing the time, yani this duration, which is in the middle of this one. It's called the transition time. It cannot be sudden change. This is like that. So actual pulses, however, are never ideal. Pulses cannot change from one level to another level instantaneously. Time is always required for the transition, yani to change the steps, illustrated in this example. So next page we'll see the practical pulses. This is a practical one. So here, as I said, so this is a baseline, and it is now changing to its maximum value. So it is taking some time to reach this value. Now this is constant. Then it is reducing to the base value. So these times, which time? This time, they are called transition times. This is non-ideal pulses. Now some definition comes here. First, rise time, which is denoted by the TR. So you should know what is rise time, what is fall time. Definitions can come, we can give you questions here related to this one. So the first question, first definition is rise time. Okay, what is the rise time? Rise time is the time required for the pulse to go from 10% of its amplitude to 90% of its amplitude. So if you look here closely, so it is the 10%. If we are saying it is A, so the 10% will be 0.1 A. So this is the 10%. And from here, it is raising to the 90% here. So how much time it is taking? We are saying this much of time. What we are calling TR, rise time. So this is a rise time. Similarly, we have fall time. Fall time is what? So it's like a time required for the pulse to go 90% of its amplitude to the 10% of amplitude. So it is a 90% value, and it is falling to the 10% here. Okay, this is called PF. Okay, this time is called fall time. Okay, now pulse width. So if we go the ideal case, guys, pulse width is like that. See, this is the pulse width. So I can measure pulse width at the base. I can measure at the top, everywhere pulse width is same. But in ideal case, you can see that pulse width is not same because it is changing with the time. Okay, so from where we should measure, this is the point, because if I measure here, it is different. If I measure here, it is different. So at which point we should measure the pulse width? This is the point here. So the rule is, the pulse width is the time between the point on the leading edge where the value is 50% of the amplitude and the point on the trailing edge where the value is 50% of the amplitude. Means is that we should measure when the amplitude is 50%. This is the 0.5a. So at that time, we will be measuring the pulse width. This is called TW. So here are some definitions which we discussed: rise time, fall time, and pulse width for the non-ideal pulses. Now for the pulses, one more definition come, which is called repetitive pulses. Now, when the word come repetitive, it means something which is keep on, repeating itself. So the pulses which keep on repeating itself. So if you look here closely, from this point to this point, this is repeating. Look here again, from here to here, from here to here, from here to here. So this is actually your actual pulse. This is the actual pulse. Okay, and this is repeating itself. Definitely it will repeat itself after a time period. So this type of pulse train is called repetitive pulse. So any waveform that repeats itself at a fixed interval, what we call that interval? Time period, is called periodic. Notice that in each case, the pulse repeat at a regular interval. And that regular interval is called the time period. The rate at which the pulse repeat is called the pulse repetition frequency. The rate at which it is, repeating is called pulse repeating frequency, which is a fundamental frequency of the waveform. An important characteristic of the periodic waveform, pulse waveform, is the duty cycle. We'll discuss about what is duty cycle. So now we were discussing about this one. Again, guys, look, this is a pulse and then it is repeating. Again, we have here pulse train, which is repeating here, 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 and so on. Okay, so these are the example of repetitive pulse waveforms. So as I said, one important characteristic of the periodic pulse waveform is the duty cycle. Okay, so this type of questions may come to calculate what is the duty cycle, calculate it, and so on. So duty cycle is the ratio of pulse width. What is that? The ratio of the pulse width, TW, to the period, T, and it is usually expressed as a percentage. So if you look the first one, guys, first example, this one, what is the pulse width? You can see that this is the pulse width, TW, yani when it is high. Okay, and then what is this ratio? TW to the period T. Okay, and what is the period? This is the period which is repeated. So we can say percentage duty cycle is equal to TW, yani the pulse width. In case this is the pulse width, in this case this is the pulse width, and what is the time? And another thing is the time period. This is the time period. So time period multiplied by 100. This way we can get duty cycle. Yani what duty cycle is telling you, out of this time period, how much time this pulse is high, like this one. This is high. Remaining time is low. Its value is minimum. It's not high. So let's have an example to find the duty cycle. This is the question for you. Determine the period, frequency, and duty cycle of the pulse waveform in the figure. So first you need to find the period. So can you tell me what is the period of the given waveform? Yes, exactly. So P is equal to 10 microsecond. Very good. Then next is frequency, F. How can we find the F? You know the period is T. We know the formula 1 over T. So 1 over 10 microsecond, any 6, okay, and it will be how much? 100 kilohertz. Okay, next they are asking duty cycle, and for the duty cycle, the formula is TW over T multiplied by 100. So how much is TW? TW any pulse width. How much it is given to you? Exactly 1 micro. And how much is the time period? 10 multiplied by 100 percentage, huh? Then you will be getting. So how much percentage is this? When you got it, it is 10%. It means is that out of this 10 microsecond, it is for 10% it is high, and rest of the time it is low basically. Okay, so this way you can calculate the duty cycle. This is the way. Okay, so this kind of questions are possible. Next, so pulse waveform we were discussing, and here it's come few categories of this one. One is called square waveforms. What is a square waveform? A square wave is a pulse waveform. It is a pulse waveform with a duty cycle 50%. Look now, duty cycle 50%. Thus, the pulse width is equal to 1/2 of the period. Yani, if this is the time period, guys, from here to here, we have this time period T. So out of this time T, half of the time it is on yani, it has some width, value is high here, okay, and half of the time the value is maintaining lower amplitude. This is like that. So square wave have 50% duty cycle. So half time on, half time off, square wave. Okay, next thing, the average value of the pulse waveform. We can find the average value of the pulse waveform. So the average value of a pulse waveform is equal to its baseline value plus the periodic cycle. So here is the formula. How can we calculate the average value? So V average is equal to baseline value. Yani, what is this baseline? Yani, this value, whether it is a starting 0 or some value. And so this is called the baseline. Then duty cycle. It is not percentage duty cycle. It is just duty cycle. Yani pulse width over time. And then the amplitude. Yani the height. How much is the height? We can calculate the average of a waveform. So look now questions. So here in this example, determine the average voltage of each of the positive going waveform shown here. So formula, we know that V average is equal to baseline plus duty cycle plus amplitude. Baseline, yani from where it is starting. So you can see here it is starting with the 0. This is the baseline. So this is baseline. Duty cycle. So we know that pulse width is 1 milli and the time period is 10. So the duty cycle is 0.1. And how much is the amplitude? Amplitude you can see 2. So you multiply with the 2. The answer is 0.2 volts. Similarly, second waveform. Here you can see the baseline, guys. See, this is the baseline. Yani, this is 1, which you put it here, baseline. Duty cycle you can calculate easily. How much? So this is total is 2. Half is 1 basically. So 1 over 2, which is 0.5. And you need to find now amplitude. So you will not calculate the amplitude from the 0. You know that because it's starting with the 1. So 6 minus 1 will give you 5, which you are putting here. And then you can calculate 3.5. Third example, baseline. So you look here, what is the baseline? -1. -1 baseline. Duty cycle, because it's a square wave, 50% duty cycle, yani 0.5. And then you can calculate the amplitude. So amplitude you can calculate from here to here. So +1 minus -1, it is going to be the 2 volts. Then you will be getting the 0 average. And you can see that this square wave and the baseline is 0. So half is above the 0 and half is below the 0. So answer will be definitely the average will be 0. So this way we can ask you to calculate the average value, and you can calculate easily by putting this formula. So you need to memorize this formula. which is that one. The average is equal to baseline plus duty cycle plus amplitude. This time you are using duty cycle as it is, you are not taking its percentage. You are using the ratio, the pulse width over time period. Next in this category is the triangular wave. Triangular wave is something like that. So the triangular waveform is composite of the positive going and the negative going ramps having equal slopes. Having equal slope, the period of this waveform can be measured from peak to peak, next corresponding peak, like here. So one peak to one peak, you can measure the time period. This particular triangular waveform is illustrated and has an average value of 0, because half is the above axis and half is the below axis. So definitely average will be 0. So here is a thing, the ramp are of same slope. So this is positive ramp, then negative ramp, positive ramp, negative ramp, and so on. So this is called triangular waveform. Okay, you can see here this is again a triangular waveform, but average value is above because it is above the 0 axis. So this is like non-average value triangular wave. One more category of this type of waveform is called the sawtooth waveform. You can see this one, sawtooth waveform. So the thing is here, the ramp here is not equal. So this is the positive ramp and this is a short duration, a negative ramp is there. So sawtooth waveform is actually a special case of the triangular waveform consisting of two ramps, one of which longer duration than the other. So this is long duration, which you can see, and this ramp is quickly coming down short duration. For example, a sawtooth wave is used in automatic testing equipment, control system, and certain type of displays, including analog oscilloscope. Here is an example of the sawtooth waveform. Notice that it consists of a positive going ramp of relatively long duration, followed by a negative going ramp of a relative short duration. It's like that. So triangular and sawtooth waveform, the slopes, maybe just give you idea how can we find the slope. I remember, I believe that you know this slope, how to get it. Here we have voltage, here we have time. We are saying positive ramp because it is increasing here. And how can we find the slope? Slope will be the value on the y-axis, which is voltage, and the value over the x-axis. This is y-axis over x-axis, then v over t. This is the slope. This is a negative ramp. So that's why we are putting minus, because it is decreasing, negative. So minus v over t. This way we can also find the slopes. So if we can ask this way, you can look here. What are the slopes? So you can calculate 10 over 5, yani 2 volts per millivolts. Here 5 over 100, definitely minus because it's decreasing. So this way we can calculate the slopes also, guys. Next thing is harmonics. And here I'm going to give the answer of one question which we discussed in the second slide of this chapter. We mentioned that by using sine wave, we can generate another kind of waveforms. Okay, that's why we called sine wave as a fundamental waveforms. So now I'll show you here by how can we generate a square wave by using a sine wave. And it is possible because of the sine waves are the fundamental waveforms. So all repetitive, yani non-sinusoidal waveforms are composed of a fundamental frequency, repetition rate of a waveform, and a harmonic frequencies. So fundamental and harmonic frequencies, I will give you example, then you will understand. There are odd harmonics are frequencies that are odd multiple of the fundamental frequencies. Now, first you try to understand what is odd harmonics. So odd harmonics are the frequencies that are odd multiples of fundamental frequencies. What is that? They are odd multiples of the fundamental frequencies. So odd harmonics are frequencies that are odd multiple of fundamental frequency. For example, if the fundamental frequency is 1 kilohertz, 1 kilohertz, okay? So we need a fundamental frequency, as I said, and I need its odd harmonics in order to generate non-sinusoidal waveforms. So if the fundamental frequency is 1 kilohertz, what will be their odd harmonics? You know the odd numbers, which is like 1, 3, and 5, 7, and so on. So these are called the odd numbers. So if you multiply these odd numbers, if you multiply these odd numbers with the fundamental frequencies, you will be getting the its odd harmonics like that. So 1 kilohertz is there already. So its odd harmonics will be 3 kilohertz, 5 kilohertz, 7 kilohertz, and so on. Getting? For example, if the so yani ki 3 kilohertz frequency in this case is the third harmonics, and fifth kilohertz frequency is the fifth harmonics, and so on. For example, if I tell you guys fundamental frequency is 200 kilohertz, is a fundamental. Okay, fundamental. So what will be its uh, like third harmonics, fifth harmonics, and so on. So third harmonics, yani you just multiply with the 3. So it will be 600 kilohertz. If I ask you fifth harmonics, 5 multiplied by 2, yani how much? 100, oh sorry, 1000 kilohertz. Similarly, seventh harmonics, and so on. So this way you can calculate that one. Now you look here, what is even harmonics? So even yani even multiple of the fundamental frequency. For example, fundamental frequency is 200 hertz. So what will be the second harmonics? Second yani multiply by 2 with the fundamental, you will be getting this. If I ask you fourth harmonics, 4 multiply by 200. If I ask you sixth harmonics, 6 multiply by 200. So this way we can have even and odd harmonics. So now hope it is clear what is odd harmonics, what is even harmonics. Now time to look how can we generate a square wave by using these odd harmonics and the fundamental frequency. So next slide will explain you here how we are getting the non-sinusoidal waves is a composite of the fundamental and the harmonics. Some type of waves have odd harmonics, only odd harmonics, and some have only even harmonics, and some have both. Now you look here closely, all of you, please focus. So here we have a fundamental frequency. And what is a fundamental frequency? This is a sine wave. You can see the pink line with the dotted fundamental. So this is a sine wave. Okay. Now we are using here third harmonics. So this is the third harmonics. Third harmonics, you can see. So third harmonics is what? Basically, if fundamental is 1 kilohertz, third harmonics will be 3 kilohertz. Yani it is 3 times of this frequency. 3 times yani within this time, if it is repeating 1 time, so this third harmonics will be repeating 3 times. It will be repeating 3 times. So you can see here, this is the third harmonics. Now this green color is basically the composite waveform. Yani it's sum of it. So when you are getting the sum of the third harmonics and the fundamental, you will be getting something like that. This is the waveforms which you will be getting. Okay. Now consider the second example. We are having the fundamental plus third harmonics plus fifth harmonics. So you see this, how you are the shape of the composite waveform. You increase further the harmonics, you are saying fundamental plus third harmonics, fifth harmonics, seventh harmonics. If you add them, you will be getting something like that. So the ideal square wave is something like that, but this is a practical square wave by adding the harmonics. If we add more further harmonics, you will be getting more closer to this ideal square wave. So by using a sine wave, fundamental frequency, okay, and some odd harmonics, we are able to generate a square wave. This is about the harmonics concept and how can we generate the non-sinusoidal waveforms by using sine waves. Okay, guys, this is about that. So this way we have done with this chapter. These are some key terms: sine wave, alternating current, period, frequency. What are these? You can just have a look here. Then instantaneous value, peak to peak value, RMS value. So this is all about it. Some definitions. You can see here the value of what is RMS. It is mentioned here. And radian, what is a radian? A unit of angular measurements. Phase, amplitude, the maximum value, pulses, and the harmonic. The frequencies contained a composite waveform which are integrated multiple of the frequency. So this way we have done with this chapter, guys. Okay. So if you have question, you can ask me now.